And also, in addition to that, the molecular conformation in molecular solid that's coming from this sigma energy distribution, not only that the molecular distance are different between pairs, so that we have to consider another distribution, that's the overlap parameter, the distance between molecules. That's the x sub j and I. This is the position of j molecule, this is the position of I molecules, and this is the distance, and so on. So that's also, we have to consider this distribution. So there are two distributions here, and the Gaussian distributions, this is the Gaussian, and the large sigma and the small sigma here. And then he applied this kind of two Gaussian distributions in there, and they applied this Monte Carlo method to this molecular system, to find out this kind of equation. Quite simple, and there are two parameters, energy distribution and positional distribution here. And it turns out that the mobility depends on the exponential of square root f, and this is phenomenologically good equations, because this is related to the reduction of energy barrier on the electric field for hopping. But this equation has just two parameters, but there are a whole bunch of molecules which have different mobilities and so on. So there is actually this kind of approach has limitations in the consideration or taking into account of molecular characteristics. In order to consider such a molecular properties, the people just apply Markus theory to describe the hopping transport, where this frequency hopping rate is described by this equation, where this H is the electronic coupling between I molecule and J molecule. So electronic coupling is necessary, so that is this case. And also this lambda is the reorganization energy, where between this donor acceptor couple and then donor plus acceptor minus couple after charge transfer. So that the molecule, the donor acceptor molecule must reorganized in order for the charge transfer to take place, and delta G is the energy difference between the donor acceptor state and the donor plus acceptor minus state. So this is nowadays this kind of approach is widely applied to correlate the molecular structure and electrical properties in organic semiconductor solid. Now let us move to the carrier injection. And I think you are familiar with this kind of charge injections, carrier injection from metal electrode to semiconductors. And if the work function of metal is higher than this valence band, or in molecular term, the Lumor band, it can easily inject charges with no barrier, so that must be ohmic contact, right? And if the work function is lower than this the Lumor band, Lumor level, then there are two ways of thermionic emission here, overcome this way, or the tunneling here. I think I don't want to go into the details of this derivation of these equations, but you can easily find this kind of tunneling junction equation in the normal semiconductor textbook to get and to find this Fowler Nodine plot is proportional to the this f here, and also this barrier height exponential of barrier height of the 2/3, and this is a field divided by electric field. So very sensitive to the barrier height for tunneling, but independent of temperature because it's the quantum mechanical behavior. But usually, normally, in normal devices, barrier height is not so big. so that the thermionic injection is dominant over tunneling injections. But in this case also, the thermionic emission equations in inorganic semiconductor must be modified to apply to metal organic interfaces, because the dielectric constant of organic semiconductor is much smaller than the inorganic semiconductors. So if you just inject the charges from metal to these inorganic semiconductors, then there is a mirror. The image charges are formed here, and they attract each other. So even this, if you just think of the width of this x sub c, x sub m, here this equation, dielectric constant is small, so that in the inorganic semiconductors field, the potential between this case is rather sharp here, so that this peak position is located very close to the interface, so easily tunnel through this to the inorganic semiconductors. But this is rather long here, large distance from the interface to the electrode. So the charges actually injected up to this point actually recombine and get back to that case. So this influence, and then that must be modified. So again, I don't want to derive this equation, but we have to have this kind of additional term for this thermionic emission in organic semiconductors. So this must be modified again here. F is considered to this term. So the mirror charge emitted induced the charge recombination, injected charge recombination at the interface. This is the case. So that's also. Now this, I mentioned that the SCLC requires ohmic contact. Also, for proper applications, we don't want that the voltage consumption at the injections. We would like to have ohmic contact. How do we realize the ohmic contact? In the inorganic semiconductor, that's done by electrical doping, heavy doping, P or N. Then the barrier region, depletion region becomes very narrow, and the tunneling is really efficient. That's one way to form ohmic contact, right? So we need also electrical doping to form ohmic contact. In the commercial devices, electrical doping is normally used. But I found that many laboratories in academia do not use this doping. In such case, the device characteristics are wholly determined by the junction or devices, but sometimes the interface, the injection characteristics becomes dominant. Then we have to find out the dopant. But doping process in organic semiconductor is quite different from the doping process in inorganic semiconductors. In inorganic semiconductors, we use the different valence atoms for P and dopings. But that is not the case here. We dope the different molecules whose energy levels is very low. Actually, the Fermi level of the dopant molecule is lower than the HOMO level of p-doping. In such case, the electron can be transferred from HOMO to the electrons in HOMO level, right? So the electron is transferred to form a hole in these molecules. So that's called charge transfer, and that must take place in the ground state. In order for the charge transfer in ground state to take place, this energy level must be very close within the thermal energy, or this energy, Fermi energy, must be lower than this HOMO case. For n-doping, reverse, and the Fermi level of n-dopant must be higher than the LUMO level of ETL, so that the electron can be transferred from dopant to LUMO to form negative ion. So the electron injection, electron formation here. So we call negative polaron, or electron here, or the negative ion of molecules. Various molecules have been introduced, and this transition metal oxide, they are working pretty well. Yeah. And the HATCN, this was developed by LG a long time ago, and have been widely up to quite a bit of time. But nowadays, I think that different dopants are used for commercial applications. Anyway, this is F40SNU. And they have a lot of fluorine atoms and cyanide to extract electrons or lower electron of them. P dopant is a different case, alkali metal or alkali metal carbon oxide or heterocyclic atoms shown here. So they have these kind of cases. And these are the cases and use. The explanation of ground state charge transfer is correct or not. We just checked. I'll show you the examples. This is MPB. This is whole transporting materials widely used for OLED. And we doped with rhenium oxide into NPB, and whose the rhenium oxide has a work function of this amount. This energy level is different for different groups and so on, but we think this is the level. And by doping, the absorbance changes and the new peaks appear. Here, this is a charge transfer peak here, we think. And it's real that the charge transfer takes place. That was proven by the IR spectroscopy of this one. After doping, you see that the new peak appears here. You see this big red one at the expense of this reduction of these peaks. Those two peaks correspond to this the para-substitute benzyl group. So this is the molecular structure. This is amine, and this is phenyl group. And then this one is breached. That means that it changed. And this new peak is related to the ion, the absorption of this compound, charged one. So there's a charge. This charge is transferred from rhenium oxide to form this the plus polariton here in this phenyl group bonding with this nitrogen here. So after doping, you see that originally without doping, the current is like that, but after doping, you see ohmic current followed by a space charge limited current at a certain point. This demonstrates the ohmic contact is formed, and then that is coming from the ground state charge transfer, as you can see here. Now I will finish up this case with the recombination process. So electron and the hole is coming, and the recombination takes place between electron and holes. There are two mechanisms. So one is the bimolecular recombination. Electron is coming and the hole is coming, and then they recombine. So in organic terminologies, there's band-to-band transition recombination. So in this case, we call Langevin recombination, or the trap charge, in some cases, trap-assisted recombinations. First of all, hole or electrons are trapped to the trap state, and then recombine with the free electron or free hole to actually form recombinations, so on. That's all called we call trap charge limitations. And for these Langevin recombinations, that is proportional to the electron and the hole densities, and then but the trapped case trapped charge times free charges, and then this is the capture cross section of electron and hole. And also, of course, this depends on the dielectric constant and the mobilities of electron and holes. Now this I showed you that the electrical properties of electron and holes and the junction characteristics for charge injection, not only the metal organic semiconductor, but semiconductor junctions, we have to apply these thermionic emission modified cases, so that in order to get the total equation from diode, it is not easy, and the numerical simulation is required without analytical equations. So for charge injections, thermionic emission and low field, and I explained already, that needs to be modified from the inorganic semiconductors, and the current flow use Poisson's equation and continuity equations for the electron and holes, and also you need to consider trapping and the trapped charge, and also you need approach model for carrier mobilities. I just introduced you just a Bessler model, but the Bessler model it turns out to be adequate for all the molecules, but so sometimes you need different one cases. Anyway, sometimes we need to use phenomenological models to get that. Also, recombination and bimolecular interactions are required sometimes, because in the previous case I also explained the triplet annihilation, triplet polaron interaction, and so on, quenching, and so on. So we need to consider that kind of annihilation processes. All right, this is the end of the second lecture. Thank you for your attention.